going to introduce my speakers. First, to my left, we have Matthew Harris. He is the Space Focus Area Lead for QinetiQ, a recognized thought leader on space infrastructure development and the integration of systems into current and future space architectures, including off-world domains. He spent 2 decades working for government agencies in areas of strategic planning, programmatic support, subject matter expertise, and that's exactly what he's going to be bringing to this discussion here, as well as some solutions planning expertise, and he's going to talk about some of his work. Thank you so much, Matthew, for being here with us. And next to Matthew, we also have another SpaceX alum, is the Chief Executive Officer of Space Tango, Sita. Sita manages the implementation of corporate mission and vision for Space Tango, and prior to that, she led the space industry practice for Boston Consulting Group, and also as the head of human space flight sales at SpaceX. She executed the first private space flight sale on the Crew Dragon on a low Earth orbit free flyer and to the International Space Station. Sita, thank you so much for being here. It's good to have you. Finally, on the end, we have James Spicer. He's the Technical Director of Kepler Communications, US. So James was the principal aerospace engineer at SpaceLink, where he transitioned the Odyssey space data relay architecture from RF to optical and was responsible for writing spacecraft specifications, requirements, an optical testbed, and link budget tool development. So we have lots of expertise on the space. James, thank you so much for being with us here. It's good to have you. So we're going to kick things off here by how many of you in the audience watched the Odysseus lunar lander landing mission live? How many saw it live on the broadcast? So we had a few over here. Nobody? Okay. All right. So we had a few. My first question to the group is, when I watched it live with my 6-year-old, this is the first U.S. spacecraft moon landing since 1972. So, first one, this Odysseus, privately owned. While I was watching it live with my 6-year-old, it was coming close, it was landing, and then there was 15 or 30 minutes where we don't know what was going on at all. It was just like, we'll be back after this very long commercial break. But here's a live feed of everyone at NASA trying to figure out what happened. So my question to the group is, why did this happen? What happened? Can you explain why we had this 15 to 30 minutes where we didn't know whether it landed? How did we eventually find out whether it landed? And how does this illustrate an example here of why we need connectivity in space? Start with you, Matthew.
So I have a 10 and 8-year-old, and we've faced the same issue, and I told them, just imagine not having Wi-Fi for a little bit, because then the crisis would be over with. So I had to try and explain it to them that, imagine, I guess it all comes down, and I'm not too technical expert, but line of sight, right? Everything to do with antennas, back to Earth is line of sight. And of course, at the time, there's no humans on the spacecraft, so you don't know exactly what happened. So you can only guesstimate that the thing must have tilted over or not aimed at Earth. So I was trying to explain to them, well, they just got to make sure that one of them somewhere has to meet something on Earth. So think of point A and point B, and that's the limitation, right, of that kind of communication. Of course, then when you can talk to the spacecraft, you can figure out what everything else, the health-wise. So I'll save the rest of the technical for you guys, but...
Sita, you want to go next?
I will be similarly non-technical. I will add to that a hypothesis, which is both a line of sight issue as well as a handoff protocol issue.
Right.
I think clearly the network that was being utilized to send and receive to ground is doing 20 million things at the same time. It's the singular solid network that is actually a vulnerability and dependency. And because there are precious milliseconds that are lost in handoff between the various utilizers, our dear friend Audie, that's what we called him, we placed bets actually on who was going to make money, that it was going to stick the landing or fail, or no one really won any money with that 15-minute window of nothing. But fundamentally, we were wondering, is Audie going to take precedence in a handoff protocol?
Right.
Chances are no. So my hypothesis is that there's a line of sight issue, as well as likely seconds adding up to minutes of decision making of who's actually leveraging the network in that moment in time or in those 15 moments in time.
Yeah, absolutely. James, what happened? Why is that important?
Well, I think one of the challenges that they had was that the lander came down onto the surface of the moon and then tipped over. And the mission was designed such that they had assumed that it would land upright with the antenna facing towards the Earth, and what actually happened, it landed tipped over, and now the antenna's pointing down towards the surface, and it's kind of like if I'm talking to the audience here, but then suddenly I turn around here and I'm talking over here. It becomes much harder for the receivers out there to pick up the signal.
Right.
So I think they made assumptions when they designed the links such that included the power of that transmitting antenna, the gain of the antenna pointed in the direction of Earth, and if the antenna is pointing over here, the gain in that direction, the power that makes it from the moon back to Earth is much, much diminished. So they had large receiving antennas on the surface of the Earth that were listening for that signal, but the signal that was coming in was much, much weaker than anticipated, and so they weren't able to get the data rate that they wanted. It was a very, very faint signal, much harder to understand, much harder to decode the signal. So the data rate had to go way down, the data science return had to go way down, and they actually had to use the most sensitive and the largest antennas on the Earth to be able to pick up such a faint signal.
Right. And those were located, was it Goonhilly? What did we have to wait? Apologies, my brain is fried, I've been talking all day. But how did we eventually...
So I believe it was Goonhilly in Cornwall, England, that was the first to pick up the signal. But I had also read that it was the Parkes telescope down in Australia, which I think is a little larger, that was actually able to get a stronger signal and be able to actually decode some of the data.
Excellent. Yeah. So again, illustrating the problem. So now we talked about what happened. How does this change? What happens when there are actually people in there? Right? Do we have 15 minutes? Or what happens then? But right, I mean, if we don't know, right, and this is why we need connectivity, right? We've just illustrating the need for connectivity. So James, I mean, you're working on this, right? So I mean, this is your business case, right?
Absolutely. So, what Kepler is doing is we're deploying an optical space data relay network to enable high throughput, low latency connectivity to any mission that leaves the surface of the Earth. Mm-hmm. So whether it's a Earth observation spacecraft, a human spaceflight mission, and that's actually a big segment of our market, all these missions need continuous access to the internet, continuous access to other missions, continuous connectivity down to users and mission operators on Earth, and whether that's in low Earth orbit, medium Earth orbit, geostationary, or all the way to lunar orbit, every single mission needs that connection back to Earth, back to the mission operators. And so in this particular instance, if the lander had landed, couldn't get signal, that could potentially be a mission critical scenario if you don't know the health of the onboard crew, and not being able to fix and troubleshoot the issue could potentially be extremely serious.
Right. I mean, we can say, anybody knows, you can't do work these days without the internet. You just can't. Anything. We all become helpless. It's kind of scary. And in space, it's especially scary, right? So that said, let's kind of, for those who aren't familiar with what exists today, like what communications networks or capabilities currently exist to connect spacecraft beyond Earth's orbit. Let's set the table, and then we can talk about what we want to build. Who wants to start here? You want to start, James? You use it. What exists now will come down this way.
Yeah. So beyond Earth orbit, I suppose we're talking out beyond LEO, MEO, GEO. We're talking mainly about lunar missions and even beyond.
Right.
And so traditionally, for lunar missions, you use the Near Space Network. NASA operates a network of large antennas, 10 to 20 meter parabolic dishes around the world that point at the moon and missions on the surface of the moon and in orbit around the moon, and you get a line of sight link. And so as the moon as the Earth rotates, you hand off between those antennas on the Earth. And the near space network operates all the way out to 2 million miles from the Earth's surface. Beyond that, you transition over to the deep space network, which operates anywhere from 2 million miles out to the edge of the solar system, essentially. So those are the antennas that talk to Mars, to Jupiter, and NASA and other missions around those planets, and in fact all the way out to the Voyager spacecraft at the very, very edge of the solar system.
Excellent. Sita, when you answer, first tell us about what you're doing with Space Tango, and what exists today to meet your needs, what you need to meet your needs.
Yes.
There you go. It's a tongue twister.
Thank you. I love a chance to proselytize about the business that we run. We historically and to date have operated in low Earth orbit. So we leverage TDRS by and large, and we do swaps and get access to bandwidth when NASA awards it to us. Now, I think it's important to foot stomp, not all activity has to be commercial for it to be a commercial provider. We are an example of a commercial provider with a commercial business model that still serves fundamentally a US government anchor customer, in this case NASA. And we've done 266 payloads and counting. We're actually launching on SpaceX 30 tomorrow, or I guess tomorrow, and counting to the International Space Station. Inside those payloads, we have a Cube Lab small sat form factor into which we introduce cell cultures, tissue chips, or organoids. We manipulate them, we synthesize and simulate a human environment in microgravity to see how cancer grows, to see if we can do layer by layer deposition to make an artificial retina, to actually enable the development of hepatocytes into a liver graft. These are real experiments that, yes, have been financed by NASA, sound like science fiction, but actually are healthcare solutions here on Earth, all on TDRS. So that's what we use now, and we are very much at the whim and mercy of both NASA's approvals, but also whenever requisite handoff protocols are made. That's why I mentioned that earlier. We get the AOS, the acquisition of signal, loss of signal indicators all the time, so that when that happens, we also have to be prepared for some kind of either network redundancy or preparation for that loss of signal. Like how are we going to make sure that that life science culture is still alive, in effect? So think about the implications for what you were just describing. There's a crewed mission on the lunar surface. Those are humans inside. You want to preserve the science of the life inside a spacecraft? We're doing that on a very miniature scale. And we have a lot of the insights, therefore, into what you do when you have a loss of signal. Right. How do you preserve the viability of science, which is said another way, how do you preserve the viability of the life inside? So the one coda to this that I think is deeply relevant in terms of what we will need is we were just awarded a $5 million contract for NASA to be on Artemis 2. And we're actually doing science payloads integrated into the Orion spacecraft that will be in lunar orbit. So we're actually going to be using whichever network is appropriate there. Historically, that's been LCRNS or LunaNet, so I fully anticipate we'll be doing that in this case as well. But make no mistake, this is one of many, many lunar missions that NASA is investing in for a permanent human presence on the moon alone. We're going to need a bigger network. Right. Fundamentally.
So Matthew, I mean, you do a lot of work in what we need in space. Tell us a little bit about some of the proposal work you've been doing, solutions architecture work you've been doing.
So QinetiQ is more of an integrator, so we kind of take what smart people are doing and, of course, put them all together and kind of create a solution out of it. And so a lot of what we're doing, like right now we work for Space Development Agency, for ComSatcom, Space Force and stuff like that, but so our mission is more mission services and Sita work and kind of technology roadmap, and again, the solution architecting of what's the art of the possible. So we're not actually bending metal. I wish we would, but we're not. So I'm going to take what they're doing, and it's a little bit kind of expand the scope, expand the horizon on it, and take these similar problems, because again, if you, same challenges, and let's just say we do have a lunar habitat, and so you have multiple different data needs. So whether it's sensors, not just for scientific stuff, but to measure the health of whatever habitat, et cetera. And I always say, I joke with people, I'm sure people on the moon will still want to watch Netflix like the rest of us. So, plug for Netflix. But, and I think about, actually speaking of Netflix, there's a movie called Spaceman that just came out with Adam Sandler.
Have you seen it yet?
I did see it.
Is it terrible?
Eh.
I've heard it's terrible.
But it shows this communication issue. He doesn't talk to his wife, and he goes absolutely insane all the way out past Jupiter because he's alone. So I think about that. If we have humans, there's another side to this. So there's your problem set. But take those natural, challenges along with man-made challenges or human-made challenges. And so what I'm trying to look at and what QinetiQ is doing is beyond the moon. So we've got to think to Mars or even beyond. And of course, everyone says, oh, there's pie in the sky. But if we can build what we want to do with this space economy, right? If we can build humanity off-world, by mid-century, by end of century, we're going to want to be out there. So we're going to have to lay that infrastructure. So that's where what we're doing is trying to think about that and work within the government to develop those requirements and figure out how to create that. Because again, you look at the economy on Earth, it's so much driven by data. The space economy will definitely be as well. So all aspects. So I don't know if that answers your question, but it's taken them a little bit beyond, well, millions of miles beyond, but yeah.
Yeah. No, I mean, but you bring up an interesting point because, people are still people in space, and the people who have been in space largely have been very itinerary and mission driven. Yeah. So their entire day is focused around achieving a mission. Right. But we haven't had people who are just doing their job in space and expect 9 to 5, and then after 5, they need to relax, right? And this is kind of when we're talking about future space economy, people doing jobs in space. This is another need for connectivity, right? Because not only can we not work without internet connectivity, we can't live. We're so connected to our connectivity that.
And real quick as a follow-up, just to go back to Sita and James's points, if you take that prioritization of network, would a Netflix override a command, override data? It wouldn't, right? Because of life safety. However, so it's by building that robust, scalable network, we can then do everything that society would require off-world.
And we'll get into some of the details of how we're going to put these networks together. And my first question on that is, just from I know we're not going to dive too deep into the technical knowledge here, but what is the bigger technical challenge overall, connecting localized networks in space or connecting those networks with networks on Earth? I'll start with you, Matthew.
So the challenges that I've been looking at is mainly solar conjunction and stuff like that. So, I mean, you take the moon example that we're talking about with Odysseus and expand even just to Mars. There's certain times of the year where you have a week or I guess it's 2 weeks, where the sun is in between Mars and the Earth. You can't communicate at all. It's just completely interference. So by building a relay network or an architecture, you would be able to have those nodes go around solar conjunction or anything else, or also go around for resiliency or to send traffic priority. So that's what, in that sense, some of the things of challenges.
Any of you want to, Sita, you want to add to that?
Definitely. I mean, it's literally baked into the name of TDRS, and LCRNS is relay, so I would absolutely emphasize the need for relay capability. I'll add to a level of complexity specific to what Space Tango does, but I think will not be unique to us in a not too distant future, which is very much automated. Our cube labs that go up to the ISS, they're not glove boxes. They actually don't require crew time. So when you're talking about the astronauts who are mission driven, they're performing tasks on ISS and have been doing that for decades, they have very minimal touch with what we do. It's literally taking it off the Dragon, putting it on the Express rack, and then it runs itself, because we have programmed a lot of those commands into the code, and it's automated and run from our ground station in Lexington, Kentucky. If you imagine that on a lunar surface, I doubt we're going to be communicating from Lexington, Kentucky, number one.
Right.
Number two, many of the processes are designed to help the sustainable life form that's required for an actual cislunar economy or anything further beyond in space, which means you're going to need to have an effective edge processing capability, which we're already studying right now on the ISS, and is very much part of the ecosystem for the commercial space stations in LEO. In fact, they all assume it is a foregone conclusion that you're going to have not only edge processing of data that's collected. In our case, the use case is science specific, but obviously there's so many different applications. But more importantly, to process that data, even so at the edge, to have a more robust relay network in that area, in that vicinity, means you're not at the dependency of a ground station in Kentucky. So
Right.
I think there will be a need for the development and deployment of antenna systems that are part of that relay system on the lunar surface. That's very much already being designed by your friends over at DoD, but it's certainly being thought by NASA as well as a redundancy for Mars travel.
There may be a few of them out there too, in this room.
Yeah, a few of these folks here.
Few of them. James, do you want to add to that before I ask you about how you're going to make things better?
Absolutely. And I think a large part of what lots of people in the industry, including Kepler, are doing to try and make this follows on from a lot of the problems, which are numerous and significant. So several of them, of course. The relay capability is key, and for those in the audience who might not know, the tracking and data relay satellite system that Sita mentioned, that's a network of relay satellites around the Earth that enable the International Space Station, Dragon, etc., to achieve 100% coverage. So wherever it is in its orbit, it can see at least one of these relay satellites and therefore kind of have a link back to the Earth. Right now we don't see that, for example, around the Moon, with the exception, and this was only yesterday, the Chinese launched their second data relay spacecraft into a halo orbit around the Earth-Moon Lagrange 2 point, and that enables the Chinese to essentially have line of sight to the relay satellite. The relay satellite can see the far side of the Moon, and this enables Chinese landers and rovers to maneuver on the far side of the Moon, and that's something that...
That's their destination, isn't it?
Exactly.
Right.
That's something that no other country has so far been able to do. Augmenting that and putting in place a network of relay satellites that orbit the Moon rather than orbit the Earth would enable landers, surface operations, users on the surface of the Moon to always be able to see the relay satellite. The relay satellites can talk to each other, and then the relay satellites talk back to Earth. And this comes back to another one of the challenges, is that so far every lunar mission, whether it's a landing mission or an orbiting mission, has had its own link back to Earth. And so for every mission, if you have 10 missions on or around the Moon, that's 10 links back to Earth across 250,000 miles of space. I think one way that the industry can move to solve this, and there are people moving to solve this, is to aggregate links on the Moon. So rather than having 10 or 100 or 1,000 links all the way back to Earth, aggregate those links in lunar orbit. So have all the users talking to local nodes, and then have one or two very, very high throughput links back to Earth or Earth orbit, analogous to undersea fiber optic cables, for example, where you don't have 1,000 undersea cables, you have a small handful of very, very high throughput cables, and everybody aggregates on the shore, pushes the data under the ocean, and then kind of disaggregates at the other end. I think we're going to see much more of that between the Earth and the Moon.
Yeah.
It's like Moon Wi-Fi versus a Moon modem.
Right.
Is what I guess, like in terms of the scalability of that idea.
That's a very good way of putting it. Moon Wi-Fi versus Moon modem.
Modem, right.
Got it. That's...
You can
yeah.
quote me on that.
So James, you hinted at this a little bit with your answer there, but you've been pioneering laser link technology to improve specifically the performance of connectivity in space. For those who don't understand how an optical data relay network works, can you explain how they work?
Of course, yes. So fundamentally, there's a big shift in the industry right now between communicating over radio links, either between satellites to ground, satellites to satellites, and then or then communicating over optical links between satellites or satellites to ground. And the real difference is that as you move up in frequency from radio up into optical, the beams get much, much narrower, and the bandwidths get wider and wider. And so the data rates you can achieve in optical are several orders of magnitude greater than those you can achieve in RF. And more importantly, for the very, very long links that you see when you're trying to communicate from Earth to the Moon, Earth to Mars, Earth to Jupiter, etc., the tighter the beam, the more efficient the link. So in terms of if you were to measure it in bits per second per joule, for example, or bits per second per kilo of payload, the tighter the beam, the further you can throw those electrons, the denser the beam is going to be on the receiver. And so this just really improves the data rate and improves the distances that you can throw those links. So far, most of deep space communications has been over radio. We've been doing this since the 1960s. But there have been some recent developments, most notably the LLCD mission by NASA back in the early 2010s, which demonstrated a laser link from lunar orbit back to Earth. And then most recently, within the last few weeks, the Psyche spacecraft sent back a CAT video from millions of miles away, again over a laser link, back to a receiver on the surface of the Earth. The challenge with optical, as opposed to radio, is that getting through the atmosphere becomes very, very difficult, because the slightest cloud or scintillation or any atmospheric effects is going to mess with the signal. And also the pointing becomes difficult because your beam is a fraction of the size compared with a radio beam. So optical technology is excellent for space-to-space links, communicating between satellites in Earth orbit to satellites in lunar orbit, etc., where there's no atmosphere in the way. And so I think what we will see over the next few decades is kind of hybrid systems, where for any space-to-space link, whether that's lunar surface to lunar orbit or lunar orbit to Earth orbit, where there's nothing in the way, that's when you use the optical links, because they're really, really good at those very kind of high throughput, very, very narrow trunk links. For the last mile through the atmosphere, where you have clouds and other atmospheric effects to contend with, that's where you use RF. And as well as applications where you don't want to point an antenna, so that's kind of the mobile phone scenario where you want an omnidirectional link, that's when you would use RF for the last mile from the cell phone tower on the surface of the Moon to the lunar rovers, or the EVA backpacks, etc., where they can't point the antennas because they're bouncing around or moving around. Use RF for those links, and for the last mile, Earth orbit to ground, but for everything else, you use optical.
So satellite transmissions continue to get smaller, tighter, more energy efficient. They're like literally like if this is RF, then this is optical and more efficient energy.
Yeah.
Okay. That's I do not understand physics as well as anyone in this room. But I understand sound, so music. So I'm thinking in visual terms. But Sita, is there anything you wanted to add about optical? Is optical something that you're looking at as an end user?
I would say we're looking at it as a subcomponent of what would be the most effective means to transmit data, fundamentally. So yeah, it is absolutely a necessary element of a successful data relay network for lunar application. It's not, it's again, like a foregone conclusion. We as an end user, similar to you, I think less about the physics and I think more about what are we doing this for?
Right.
What is the economic value? And at the end of the day, this is the future space economy. It is not just research missions for NASA, which has been the bread and butter for a company like ours, but it's research missions for NASA to inform our understanding of humanity, not only how it survives here, but also our understanding of other species, known and unknown, and also how fundamentally, to speak very narrowly, how we will survive on the lunar surface. So yes, for sure, we're going to need optical links to be able to have that robust relay network in a lunar environment if we want to go beyond the LCRNS to this really informed LunaNet, and that LunaNet is currently in development. I think we also need to remind ourselves what the use case is, like why are we doing this and what economic value can be created as a multiplier effect so that it's not just science for science's sake.
Okay. Matthew, at QinetiQ, you are currently working on a deep space communication architecture concept.
Yes.
You've briefed the White House Office of Science and Technology Policy that's passed November. You've told me you're working on a proposal for DARPA.
Yep.
Can you tell us a little bit about the concept you're working?
So it's taken very similar, so a combination of optic and RF. But so I'm more, again, I'm not an engineer, scientist. I'm gonna take a step further into policy and into poli-sci. So I'm a student of military history and strategy. So if you think about your days of Mahan and sea lanes of communication, right? It defined a whole era of where we set up coal stations and all this stuff of how we could get across the Pacific and do trade, war, etc. So it's taken the optics, taken the radio frequency, the line of sight type problem, but how do we go throughout the solar system? The solar system is constantly moving. It has gravitational eddies and stuff like that, and all the physics. So we're trying to look at a new concept of using the Lagrange spots throughout the solar system and almost parking a buoy or parking relays in fixed locations to allow spacecraft that's traveling throughout the solar system, or whether you're a facility on a celestial body or an end user, they know a fixed spot they can point at, and then within that point, because the Lagrange spots are fixed, they can then connect that relay network throughout the solar system and achieve the resiliency, redundancy, robustness that we're talking about, and get around all the various challenges that the solar system offers. And like I said, it's really interesting because people always try and draw the solar system as like a 2D map, and it's, again, like I said, I actually met a girl last summer who's trying to mathematically calculate these gravitational eddies as her PhD, and it's amazing to think of them as the highway. So again, whether you call it a slingshot or whatever your Holman transfers, they're all going to be different as we're going throughout the solar system and back. And so if we're having caravans of people and commerce and mining materials, as I think about it, 50 years, all this stuff needs to be able to be connected between its endpoints, between itself. So if there's something of an emergency, humanitarian issue, you as a ship can go aid and stuff like that. So all that stuff could be possible if we try and like I said, we're looking at it as that novel concept that I briefed the White House, and then for DARPA is, can we use these Lagrange spots just as much as the Chinese did Lagrange 2, Earth Moon, but there's various ones between the sun and Earth and et cetera that can help.
Yeah. You're setting us up for our next panel, cartography in space, right? That's
yeah.
No. But anyway, no, that's awesome. Sita, as our end user in space, I know high performance connectivity is critical to your business, but you are also planning an automated in-space manufacturing operation. And what makes this, when I hear that, what makes this special is that you're trying to do you're trying to literally build an IoT network in space. You need both a powerful pipeline of connectivity into the network, and then connectivity for your IoT network within the facility. How do you do that in space? How do you obtain that in space?
With a good network, first and foremost. I'll talk about the use case of what would be required for an in-space manufacturing facility, and that gives an indication of how much data transmission would be performed as a performance requirement, and what some of the systems are in development that could enable it. So right now, NASA's SwampWorks is in the process of developing a 3D lunar regolith printer to manufacture lunar infrastructure. That lunar infrastructure requires the capture, reutilization, and repurpose of water as well. These things that we've kind of taken for granted as not only prerequisites, but readily available technology that we can just build here, simulate, transport to the lunar surface on one of these rovers eventually, and then start building there. But then it's and then start building their piece, which is where we believe we will be a real key groundbreaker, because what we do on the ISS in much smaller form factors is, as I said, entirely automated. We can introduce fluid into an environment, an austere environment. We can control the temperature in that environment, the pressure, the convection, the buoyancy, so that what we introduce, whether it's fluid to solid, solid by itself, we can actually manipulate how it grows. That knowledge there aren't a lot of providers in this space that actually meet that need. But you can translate that from one orbital environment on, again, leveraging TDRS bandwidth that's been made available to us when we ask for it, but only on occasion. If we want to do that with limited connectivity on the ISS, the challenge that we have placed before us is how can we take that into a lunar environment, leveraging what LunaNet will be. So the data transmission requirements will be greater. Right now, even to manage and observe those 4 scientific properties that I was mentioning on the ISS, we have an automated system that will detect you're outside that ideal window of temperature, or you're outside that ideal window of pressure, and it will send a ping onto a Slack channel that 4 of my teammates, myself, we will get in real time, and it will say, okay, now we're also self-correcting.
Right.
That self-correction on steroids on the moon is a level of not only data requirement, but processing at the edge that is in effect a form of IoT.
Yeah.
We're not building the network ourselves, right? Mm-hmm. But we are going to be, as I imagine, a provider for NASA. So it's going to be on NASA to make sure that their moon version of TDRS has the redundancy required so that we can build at scale, because what we're building now is minutia compared to the kind of building that we would need to make in that environment.
Yeah, absolutely.
So, I mean, I wanted to say what I loved about your concept is it kind of reminds me of a bunch of lunar gateways.
Yep.
Right? They're quasi-fixed entities, but those fixed entities are deliberately meant to be pathways forward, and you're designing them in a way to serve as, if I'm not mistaken, a data relay system in and of itself for deep space. And if you're designing them around the moon, I would love to learn how you're designing them, because we would be the end user at the end of the day, right?
Yeah, absolutely. If you have questions for our speakers, start thinking of them now. I'm going to go to you in about 5 minutes. We're going to dedicate all 15 minutes to audience questions. So please think of some questions to ask, because we'd love to get your thoughts on here. I want to bring this up to the group before we go to audience Q&A, but let's talk about developing dual-use connectivity in space. Government and commercial military dual-use connectivity networks. What are the challenges there, and why is it important to talk about this challenge? Let's start with you, Matthew. We'll go down.
I mean, I think right off the bat, you think about Starlink and Starshield, for SpaceX's network, and right there, I mean, it's the same network-ish, but you still have to segregate your government military from your regular, commerce, civilian usage. And I would imagine, even on the moon or beyond, you're going to have various actors, whether they're, government or civilian, but then also international, and this is where it really throws the policy and regulatory hat on of how do we, if you're a U.S. company managing some kind of network, be able to play nicely. Is it like PNT using GPS, where we will not turn off the P code and stuff like that, but it's still a U.S. system, so of course everyone else builds their own because they're worried about it. But and that's where I feel like I don't want to go down the road of the prioritization, because again, then you'd be like, well, who gets priority? Is it the government? Is it the civilian? Or international? But it
I'd
also
say this is the one job I never want.
your air traffic control. You're deciding, but that's where it's going to have to be. So before we talk about mission, now you're talking about actors, right? And not just within our own country, and a lot of us wear a military hat, but then bring in international partners, or maybe not international partners, just international people who want to use our network. And how do you keep that segregated, firewalled off, and still give them, if they're paying money, the same bandwidth or the same throughput that they desire? So,
yeah, absolutely. James, dual use, government, military, what are the challenges in this space?
Yeah, I think, as Matthew mentioned, cybersecurity is always going to be a big one, because the government and militaries, by necessity, have more strict, more stringent cybersecurity requirements than on the commercial side and on the civil side. So I think part of that is being able to accommodate traffic, having a single network that can accommodate traffic of different types. And I think part of that is also changing the mentality for the very, very strict military users who are used to NSA Type 1 encryption on everything. But they still use the terrestrial internet to communicate between the different nodes around the world. They just very, very heavily encrypt the data before it even enters the terrestrial internet. And I think fundamentally that's where we will end up. They still use those undersea fibers. They will still use the infrastructure that is being put in place currently between the Earth and the Moon, around the Earth and around the Moon. And I think you're just going to see a lot of the military and the more secure users just using the very, very heavy encryption at the endpoints. So encrypting it heavily before it enters the network and decrypting it on the other end once the packets come off the network. And as an internet in-space provider, Kepler, for example, we just act just like the terrestrial internet, just like a Comcast or an AT&T. We take in packets at one end, we spit out packets at the other end. We don't know who those packets come from, where they're going, what they are. They could be voice, video, text message, etc. So I think that's what you're going to see, and it's just a matter of making all the different users comfortable with the ConOps and making it clear that data security is a priority, but as just a packet switching network, the infrastructure doesn't necessarily have to be super duper secure in itself.
Yeah, absolutely. Sita, do you want to add anything to this before we go to our audience?
I do, and I think dual use is an interesting filter through which my real concern comes up, which is monopolistic behavior of the providers or the developers of the network. What I mean by that, TDRS is going to evolve into CSP. We've seen who the winners are that are either the satellite manufacturers, operators, and providers of the service. The user, NASA/US government, is shifting from government-owned, government-operated tracking data relay system into a not government-owned, commercially owned, commercially operated, sold as a service to a government set of users. I suspect when we talk about the development of a deep space network, you're going to have probably one provider, maybe two if we're lucky. And when you get into a monopoly or duopoly of provision, you not only have problems when it comes to pricing, but more importantly, monopolistic behavior on capacity, availability.
Yeah.
So it's not just a matter of the government saying, like you said, someone's going to do the air traffic control of, is it going to be Netflix first, or is it going to be, actual like spacecraft control, space situational awareness, for example, or is it going to be preventing an ASAT test warning system? Those handoff protocols are, okay, the government makes that decision, that's a national security decision. But if we're talking about dual use networks, what if the provider is so monopolistic that they only dedicate so much capacity for commercial utilization?
Yeah.
It's not just, is the information secure, but is the network available to be utilized? That, I think, is a real risk that folks aren't really thinking about. We're starting to see now with our dear friends at Starlink. And I think it's probably going to be even more of a risk as we develop both the handoff protocols, but also the capacity availability in a deep space network.